speak up. So, Michael, let me turn the program over to you.
Thank you, Rosa, and welcome everyone, and welcome Dr. Siegler. So I want to introduce, he likes to go by Timothy or Tim, and Dr. Siegler, he came to my attention and our attention after his presentation on Perovskites to our sister Texas, that's TXSES chapter, Solar Austin last March, where he was well received with his presentation. And this was shortly after national and international news that perovskite technologies for solar cells had advanced significantly in regards to both energy conversion efficiency and safety towards environmental safeguards at the end of life recycling. In fact, one of our own local companies, which is Hunt Perovskite Technology, was acknowledged for their leadership with NREL, which is DOE's National Renewable Energy Lab, in founding the US-based consortium known as US-MAP. And they're focused on the development of metal halide perovskite manufacturing technologies. So a little more about Tim. He is a postdoctoral researcher with the Department of Chemical Engineering at the University of Washington. He has 9 years experience working on experimental solution process photovoltaics, authoring 11 papers on hybrid inorganic perovskite humidity degradation, tandem photovoltaics, and solar relevant nanomaterial synthesis and device architecture. So I think he knows his stuff. He received his PhD from the University of Texas, Hook'em Horns, at Austin in 2019, working for Dr. Brian A. Cordial in the Makeda Department of Chemical Engineering. He has also worked in quantum dot PV materials development with Dr. Prashat Kamat at the University of Notre Dame, and Dr. Thomas Ben, I don't think I pronounced that correctly, at the University of Munich. His current research interests involve using machine learning to accurately predict degradation lifetimes of compositionally diverse perovskite material systems and devices. So I proudly present Dr. Siegler to present his topic, All the Solar That's Fit to Print, Progress and Prospects of Perovskite Photovoltaics. Thank you, Tim.
All right, thank you very much for the kind introduction and for, inviting me here today to talk. It's always great to be able to present on this very exciting research field to people who might not be experts in the area. Before I get started, everybody can see and hear me properly, correct? There are no technical issues?
Yes.
Okay, perfect. Yes. Thank you all. All right, so again, like Michael said, I am Dr. Tim Siegler. I'm a postdoc at the Hill House Group at the University of Washington, formerly of the Brian Cordial Group at UT Austin. Let's get started on what perovskites are and their potential and their future in, where potentially you could purchase a perovskite solar cell moving forward. Before we get started into the technology, though, I think it's important to look at the history of where perovskites came from and what kind of technological need researchers hypothesized such technologies, perovskites and similar technologies, could be filling. And to start this off, I think it's good exercise to think of what people imagine or what the common notion of a solar panel is. Now, you all are very familiar with solar panels and NTREG. So you guys probably know already, are very, very intimately familiar with these rigid, heavy, thick, inflexible panels that are dotting rooftops and abandoned ghost pastures around Texas, around Washington, the United States, and increasingly the world. Those of you who are more physics inclined might also know that these solar cell materials, the actual absorbing materials that take incident light, excite electrons, and convert those electrons to current, also need to be perfect. And when I say perfect, I mean at the atomic level. When electrons are excited by light, if an electron sees an atom where it's not supposed to be, or sees a different atom, let's say in silicon, it sees a gold atom in place of where a silicon should be, or it sees a silicon atom it sees a nothing where a silicon atom should be. these electrons are very strongly attracted to what we call these defect states. And when the electron is attracted to these defect states, they can lose all their energy and therefore not be able to be extracted as external current or with a high voltage, meaning that you have less efficient solar panels. This has been the problem that has plagued silicon solar technology historically, though not presently, because of the fact that you have to have this atomic perfection through the semiconducting material, not so much through the metallic contacts, but through the semiconducting material, you have to have this atomic perfection. However, silicon is not a very good absorber. It's a very inefficient absorber. So you need a very thick layer relative to other types of solar materials in silicon to make sure you convert as much of your incident sunlight as possible to electricity, which means your electron has to travel this very long distance with near atomic perfection, and creating perfect materials is very difficult to do. Despite this, however, silicon is still the dominant PV technology, as all you are familiar with. 96% of global market share in 2017, according to Fraunhofer, a record efficiency of that is second only to the prohibitively expensive gallium arsenide cells, and just continual, record-breaking performance out of silicon. And despite the challenges, the technical challenges with making a silicon panel and an absorbing device layer, you see that silicon has been able to meet the challenge of reaching grid parity with other types of generation technologies. With solar PV, again, which is largely represented by silicon, achieving generation parity on cost with other types of conventional technologies, and other types of renewable energies as well, with an exponential decrease in cost over the last decade and beyond. And these decreasing costs have in turn led to record deployments year over year. Now, as a panel researcher, it's interesting for you to see exactly how this is happening. It's happening in three major areas: lower cost of the panel itself, lower cost of the manufacturing process, higher efficiency in the solar cell, which is not an obvious driver of cost until you think about, well, if I can take the same panel I've been making for a while and not increase the cost of fabricating the panel, but get more electrons out of it, the electricity becomes cheaper from that panel, even if the panel itself does not get cheaper. And then reliability is a similar type of thought experiment where if I have to replace my panels less frequently, I get more value out of the electricity, I get more electrons out of it for the same fixed cost. So we have a solar technology that works. Why do we need another one? This is a very good question that I'm not even sure I'm very well capable of handling. But I think that every sort of technology space has the possibility for disruption in some way. And so I think that and many others in this research area also agree with me that there's a way to disrupt solar by moving away from the commonly held assumptions that you have when you picture a solar panel in your mind. Instead of having these thick rigid panels where you require experts and construction workers to install them on your roof, how about a stick and peel or peel and stick solar panel I can buy at Home Depot and install in an afternoon? Or how about solar panels that come rolled up like a garden hose that I can take my truck, roll in and out like this? Or maybe it's a commercial product like a solar phone charger I can put in my pocket. Or maybe even I can make solar cells that aren't very efficient, but so cheap that they can be used as single-use solar cells that I can dispose of after one try. Basically powering low power applications such as Internet of Things, sensors, and the like. It is with this idea, and also because these technologies were invented in the 80s when silicon was still very expensive, that researchers started to think about moving away from silicon and going towards materials that had very efficient absorption effectiveness to try to create solar cells that were 100 times thinner, at least in the absorbing layer, than the silicon itself. This allowed you to potentially have increased flexibility of your solar cells without having to change the material properties at all. Just by virtue of making a thinner layer, you can increase your flexibility. The issue, though, is as you got to these thinner films, you can't, the way of having these panels in the world changes. Thin layers, about a micron or two in thickness, cannot stand by themselves, really, like a silicon panel can. So it needs some backing, what we call a substrate. And because these bulk thin films, CadTel and SIGs, there's a little asterisk next to SIGs, but nonetheless, in general, these bulk thin film technologies required high temperature processing to like 500 C or higher to get the highest efficiency devices. You could not find a backing material that itself was flexible, but wouldn't melt or vaporize when you had very high temperature processing needed for the CadTel, for the SIGs, and other types of thin film technologies. And so it's in this mindset that some chemists, some materials chemists, had the thought experiment of using solar inks, essentially trying to, instead of using the tried and true electrical engineering ways of making a solar cell, what if there was a solution? What if there was an ink, a paint of some kind that you could have your solar cell pre-synthesized, dissolved in this ink, and then you could deposit this solar cell as easily as you could, say, newspaper or a spray painting process or things like that. And that was kind of the dream for a while. The idea would be that even if it took a high temperature to synthesize the ink itself, the deposition could take place at low temperature, meaning that you could use any backing you wanted, any substrate, plastics or paper even, and have as much flexibility as your absorber layer could handle. The first such motif in this ink-based technology, I think it's very interesting, was the dye-sensitized solar cell. And I think it's interesting because it kind of mirrors the history of the way humans have used color and tried to use the sun in prehistory. Our very first, the first things we used to color fabrics and dyes and fabrics and things and walls and things like this were with molecular dyes. And the first solar inks that we tried to use were similarly molecular dyes. These dyes have very high absorption efficiency in a very narrow absorbance window, but still very high absorbance efficiency and can take sunlight and excite electrons very, very easily. However, the problem is in these dyes, the electrons get excited, but they can't move. They're stuck inside each individual molecule where an electron is excited. So Swiss chemist Michael Gretzel, yes? Okay. Swiss chemist Michael Gretzel in 1991 had this idea that instead of relying on electron transport through the dye, you could instead take the dye molecules and put them on a electron conductive surface like titanium dioxide. That way the dye could absorb your light, but then you use a different material that's more conductive to transport the excited electrons out of your circuit into an external circuit. The issue, though, with this system, even though it was very clever and very intelligent, was that it is an electrochemist who invented this, which meant that you actually had to complete the circuit this liquid junction sort of redox couple. So this electrolyte is literally a liquid material, as you see here. So this was problematic for several different reasons. One is that charges moving through liquids and particularly across liquid-solid interfaces are very slow. And so you can't really get effective charge transfer across these interfaces. And secondly, just think about it from a deployment standpoint. You have these liquids that you're trying to put in a field if you were going to do this. What happens when the liquid dries up? And the solar cell doesn't always recover when this happens. It's not really practical to be putting dye-sensitized solar cells in the field. But I think the legacy of DSSCs, as they're called, is more about chemists thinking and material scientists and chemical engineers saying, hey, we have something to contribute here. this isn't just a problem for the electrical engineers and people who are physicists. This is something that chemists can wrap their head around as well and start working on. So chemists trying to create solutions to this problem decided to move away from dyes to other types of absorbing materials. And the first type of material they chose were quantum dots, tiny nanoscopic bits of semiconducting material that, when capped in an organic surfactant layer called the ligand commonly, could be dissolved in a common ink like dye and printed like newspaper potentially. The advantage of quantum dots compared to dyes is that while their absorbance efficiency was a bit lower, it could be over a much broader spectrum of energy, similar to a traditional silicon or a thin film technology, meaning you could absorb way more light in a way thinner layer. And so the quantum dot solar cell was invented in part by my old advisor, Prashant Kamat. It still required a high temperature sinter and a liquid electrolyte, but and so it still did, it in the liquid form did not achieve the efficiencies needed to commercialize. However, solid state versions of this architecture have recently achieved 16% and still are showing some promise for certain applications. But it is in this sort of academic environment that perovskite solar cells came about. The idea that we were trying to get materials that have broad absorbance and put them in these dye-sensitized solar cell architectures is what inspired Tsutomu Miyasaka from the Towan University in Yokohama, Japan, to try to utilize these interesting new perovskite materials as an alternative absorber. The reason he wanted to use perovskites is because he didn't know how to make quantum dots very well, at least at the moment. And his thought was, well, let's just find a bulk semiconductor that can dissolve in a common solvent, and then that becomes our ink. Instead of trying to use nanoscopic bits of semiconductor that we've synthesized already, let's take all the precursors of the absorbing material and put that in a dye, and then deposit that. When he did this, he shockingly, the very first time he he and his research team tried to test these solar cells, they were getting between 3 and 4% efficiency, which doesn't sound very very large right now, but for a material that you're trying to use for the very first time, that is amazing. By the way, I do realize I forgot to, at the beginning, define PCE. So PCE is power conversion efficiency. It is a more specific term than just saying efficiency. A lot of times efficiency can be used, or rather I say misused, as it means several different things depending on exactly what you're talking about. Power conversion efficiency specifically refers to power of electrons out generated by the solar cell, divided by the power of the incident light that comes in, the radiant energy of that light. So that's what I mean when I say PCE going forward. Apologies for not clarifying that earlier. So moving to solid state devices. So the problem with this initial paper, the very first perovskite solar cell, is his research team, by their own admission, had to construct and test these solar cells very, very rapidly. Basically, they were still using a liquid junction. And so they deposited their perovskite materials, they encapsulated it inside this liquid junction electrolyte, and then once the perovskite was exposed to the liquid, they had to run to the testing equipment as fast as they could to get a reading, a current reading, a voltage reading, before the material completely dissolved into the electrolyte. And so it was apparent, not just from a stability argument, but even from a performance argument and getting a good measurement of the system, that a move away from liquid junctions was really necessary to realize the true potential of the system. What wasn't expected was how effective this move would be. Some of the very first people who attempted to make this material all solid state, or these devices all solid state, had insanely productive results. Henry Snaith at the University of Oxford published very recently after the Miyasaka report a 10% efficient solar cell in science using perovskites, though I do love this article because you can tell he spent a lot of time and burned a lot of devices getting to that point, but nonetheless, he was able to do it. Separately, Namgyu Park from Sungkyunkwan University in Korea used the exact same solid-state electrolyte as the Snaith report, separately from Snaith, and was able to get almost 10% on a much larger area device than Snaith. From there, researchers saw that we had a result, a really awesome result, using the same material in 2 different parts of the world with researchers that were not communicating with each other. And so they saw a great opportunity to try to move this field forward and move it forward, they did. The number of years it took for perovskites to reach milestone efficiency metrics is unprecedented in the history of PV technologies. A normal PV technology takes between 10 and 25 years to reach 15% efficiency, between 20 years or in some cases a lot higher, more than this to reach 20%, and usually doesn't reach 25% efficiency unless there's a lot of research effort going into it. Perovskites have achieved all 3 of these efficiency metrics within the span of a decade. And so this has been sort of the reason why people are so excited about this material, because efficiency is no longer an issue for these solution process materials. Truly an amazing feat. And today, perovskites have the 3rd highest efficiency of any solar technology, an extremely active research area. There's, if you want to learn more, there's 30,000 very scientific publications I could recommend to you on perovskites, and a burgeoning startup community as well. It's also attracted a lot of media attention from several people, including this Mike Scott report from Forbes in 2018, which I still very much like, because despite these, these record pace that perovskite technology has taken on the efficiency standpoint, he still says that perovskite solar cell technology, and he laments that it has been stuck in the lab for a number of years. So I guess no matter what you do, you still, some people are going to be impatient no matter what, but that's okay. We're used to this as researchers. So I've explained the history and where we are now, but what is a perovskite? What are we talking about when we say perovskites, besides just this amorphous technology that's out there? Well, at its base level, perovskite is actually this mineral that has nothing to do with solar whatsoever. It was a calcium titanate discovered in the Ural Mountains by Lev Petrovsky, which is where the name comes from, in I think in the 1840s or 1880s. I forget exactly which one. And the mineral, so why do we call the solar material a perovskite if it's this mineral that has nothing to do with solar? Well, it's because we're material scientists and we're nerds. And hold on, okay, yeah. And whenever we see, using X-ray diffractometry, an interesting arrangement of atoms in a crystal, we take every material in nature that has the same arrangement of atoms and call it the same thing, name it after the original material that we found that had that arrangement of atoms. So while the perovskites that you know and that we know are just solar materials, are not calcium titanate, they do have the exact same atomic arrangement as calcium titanate. Our perovskites, though, have an organic A site, usually methyl ammonium or formadidium, and sometimes a little bit of cesium, 40% cesium in your system. A B site consisting of lead and sometimes a bit of tin, and an X site consisting primarily of iodide.
Hey, Angel.
And
sorry,
then,
I missed your calls. I decided
sometimes
to
chlorine
take
as well.
David Franklin, could you please mute?
Yeah, I started to, and then like a second later, I figured, it had been 4 hours since Buddy had his last walk.
Okay, anyway, I put him back in the waiting room. It's fine. Okay, so photovoltaic perovskites. Let's see. Okay, photovoltaic perovskites. So the classic perovskites that we're going to talk about, and you should think about when you think of perovskite technologies, are perovskites like methyl ammonium lead iodide, or MAPI, methyl ammonium lead bromide, or MAPBr, formadidium lead iodide, FAPI, or formadidium lead bromide, FAPBr. And they're commonly referred to by their acronyms for just because of how long these names tend to be: MAPI, MAPBr, and FAPBr. So what makes perovskites special among all types of solar absorbers that people have tried to use? And they have used quite a few. Well, the bulk material can dissolve very well. This is why Professor Miyasaka wanted to use this material to begin with. I defy you to try to dissolve a silicon panel or a cadmium telluride solar material in any kind of solvent that won't immediately kill you. It's very, very difficult to do. It's almost impossible, I would say. But perovskites, you have a wide choice of different organic polar solvents that you can dissolve the perovskite in to deposit it in any which manner you want, whether it's spraying it on like spray paint, printing it in a blade process like you would a newspaper, or any type of deposition method you want. Interesting and unique to perovskites are this amorphous idea of defect tolerance. Now, I don't claim to know why defect tolerance is so high in perovskites, and there's a huge debate in the community about exactly what this means. But it appears that all the atomic imperfections I talked about very much at the beginning of the presentation, having a dramatic impact on solar cell performance, aren't quite as predominant in the perovskites themselves. Perovskites have this huge ability to shield or protect excited electrons from these atomistic imperfections, making sure they don't get trapped in these imperfections and result in loss of energy. Finally, color tunability, which for those who have more physics background, I'm talking specifically about band gap tunability, but the ability to tune the infrared color of the perovskites allows you to use them in a bunch of different applications that you can't use in material systems that don't have this flexibility, like silicon or cadmium telluride. The major issues associated with perovskites, I'd say the main one is kind of very analogous to its main benefit. While I wouldn't say perovskites dissolve in water vapor and other gaseous species, it does certainly decompose very easily for much the same reason that it can dissolve in common solvents very easily, because of its highly polar nature. This means the material is incredibly unstable when it compared to other semiconductors, particularly in humidity conditions, or when exposed to the combination of oxygen and light, where light can ionize oxygen and sort of act to decompose the perovskite as well. A second issue that may or may not be a problem is that the best lab methods are not always the best industrial methods. While in theory, you could deposit this material any which way you want from an ink, there is, in practice, really only one way to make the highest efficiency solar cells possible. And this is not a scalable process. I'll talk about this in a second. And then finally, the lead content has been a significant issue. Well, I'd say sequentially, it has been an issue, has not been an issue, and then again, recently has become a little bit of a point of concern for the community again, and we can talk about that a little bit as well. So as I mentioned, perovskites can degrade very quickly, particularly in humidity conditions. And throughout this part of the presentation, I'm just going to pepper in a couple of my results. It's fine if you don't understand specifically what's happening, but I just wanted to show where my research kind of has fit in the past to this area, to like the general perovskite community. And what I've shown at the University of Texas at Austin is that you can improve humidity stability at high humidity conditions with bismuth, a little bit of bismuth replacement of the lead. Interestingly though, we saw that we had a stabilizing and destabilizing effect, where bismuth destabilized the material at more moderate humidities, but stabilized it at high humidity conditions. This is the first sort of report of an additive having a stabilizing and destabilizing effect at once. This, I think, is a very important result for folks who are trying to warranty perovskite solar cells or moving forward. For traditional silicon cathode technologies, warranty tests are performed at high humidity, which is supposed to act as a proxy for as a sort of time accelerant whereby you can simulate long-term degradation of your perovskites at very short time, or not perovskites, other solar technologies at very short times. And we're showing here that we have different degradation mechanisms at this high humidity versus at more moderate humidities. Maybe this is not the right way to move going forward. The perovskite materials are actually so unstable that with a little bit of compositional engineering, I don't want this to, okay. With a little bit of compositional engineering, you can actually utilize the degradation of perovskite and the associated color change for other energy-related applications. In a paper in Langmuir, I recently showed with a bunch of coworkers that you could take dark brown nickel iodide films related to perovskites, but not perovskites, and expose them to air, and they were so unstable in humidity that within about 5 minutes, with more rapid kinetics at further cycles, you could get this clear, colorless film that you see here. This colorless film could then be, at very mild annealing conditions, about 30 to 40 C or about 90 to 105 degrees Fahrenheit, heated to return back to the dark black phase. And you could repeat this process as many times as you wanted. And so essentially, I was able to find a thermochromic window material, an energy efficiency applicated material, just by taking advantage of how the very low humidity stability of these types of material systems. Now, for state of the art, there are many, many people who are working on the stability problem. Many, many, many people. And so there's a lot of reports out there that have really, achieved really high, impressive performance metrics. 1,200 hours of continuous operational stability, which doesn't sound very long until you realize, well, I want to actually graduate and get my PhD if I'm a grad student who is trying to publish something. So 1,200 hours is about as long as I'm willing to wait before I need to take something to press. Perovskite solar cells have also passed the standard IEC test. The one that I was talking about might not be representative earlier, but still it's a very impressive thing that they're able to pass these IEC 85 degrees C, 85% humidity tests that is the gold standard for silicon and CAD-TEL reliability. And there's even startups out there that claim that they have 25-year warranty level stability, and they'd be willing to take any commercial product that they're going to, in the future, offer and put that level of warranty on it. Although I guess it has to be seen to believe to this man's eyes anyway. As far as scalability, perovskite deposition is normally, for the highest efficiency devices, if you go to the National Renewable Energy Lab efficiency chart, which is like a sort of Bible for photovoltaic researchers, you'll see all these records, and all these records are usually achieved in a spin coating process, a way of making very nice, perfectly uniform films very easily on small area devices. These spin coating processes are unfortunately not super scalable. It's hard to do have the same level of uniformity on a large area device, and furthermore, it's a batch process. So you have to take each individual substrate that you're going to spin coat, put it on on this rotary head, and let it sit for about a minute for each time you want to deposit your system. So it's not very high throughput to do things this way. To this point, I didn't actually try to make alternatives to spin coating a possibility. Others have done this much better than I have, but I was able to show that you could get very nice control of the atomic orientation of your perovskite by adding a little bit of silver in there, which is something that folks who are working towards beyond spin coating processes could use to make uniform films for high area devices with high throughput. As far as state of the art for scale up, I'd like to show this video from Solid Technologies that shows you, now I know videos aren't great on Zoom, but it shows you basically I call this a PhD worth of solar cells. The number of solar cells that this machine is making in 30 seconds is very impressive. And you see this very large area deposition process, not based on spin coating, based on this spray process and a hot plate that makes perfectly uniform, wonderfully looking honeycomb patterns of panel size patterns of perovskite solar cells. So I'd say maybe the takeaway here is that scale up, while it was a concern initially, might not be an issue anymore. Yes, you might have some efficiency losses when you move from a spin coating process to such a process as I showed, but maybe those losses aren't insurmountable. Finally, governing lead toxicity. Initially, researchers in the community dismissed the concerns that people had when we were talking about using leaded materials for rooftop solar. After all, you have more lead in your car battery currently than if you were to fill your entire roof with perovskite solar materials. Furthermore, this report in JPhys Chem from 2015, which doesn't seem like that long ago, but in the perovskite world, this is from an eternity ago, showed that even in the worst case scenario where you had a perovskite solar panel completely fail, have all encapsulation completely delaminate, and have bare perovskite exposed to rain during a monsoon, while you would completely destroy your absorbing material, the lead would not necessarily leach into groundwater. The components that were the most soluble were the halogen component and the organic component. And the halogen component, you have some toxicity components there, but the lead largely stayed affixed to the surface as lead oxide and other types of oxidized lead products. There was a little bit of lead that leached into the groundwater, but not a significant amount. However, recently, a German group publishing in Nature Communications kind of challenged this notion and showed that even though there isn't that much lead that actually leaches from the panel into the soil, whatever lead does leach is extremely bioavailable and can be taken up very easily by plants that are planted in the area where the groundwater runs off. There are some caveats to this study. One, they use mint leaves as a sort of proxy, and mint leaves are famously in the in biology communities really famous for their bioavailability to any sort of heavy metal. And furthermore, this was a worst case scenario without any sort of safety concerns, any sort of mitigation or fixation strategies that could be used in an actual panel to make sure no lead escapes the panel in worst case scenarios. But nonetheless, it's something we have to contend with and not dismiss out of hand as researchers going forward. Okay, so I guess the last thing is so you got the science, you have the history. Now let's see, will you ever be able to buy a perovskite device? What are the economics? Can you ever, will this ever be a thing, or will this be a flash in the pan, a passing research fad? And the problem is, the reason that I might say it is a little bit of a passing fad is because of the dominance of silicon. Silicon is more efficient for now. I think this is probably something that's not going to make it through the end of the year, but who knows with coronavirus and research being a little bit arrested because of that. It's beating fossil fuels on price in many markets. When perovskites began as a research topic in earnest, this was not a given by any means. And so the cost argument that researchers had used for decades in the solution process PV community completely faded, totally faded essentially by 2015. And developers are comfortable with silicon. So basically, even if you can get perovskites to be at the same cost and performance metrics as silicon, silicon breaks the tie because of familiarity, and developers know what they're dealing with silicon, where perovskites might not be as familiar. I don't think researchers in my field really appreciate this last point as much as they can. So how can perovskites become ubiquitous in this field where silicon is so dominant? And I think it's about reframing the problem, not as will perovskites displace silicon, because I think the answer is no, probably never. But there are other paths to commercialization where perovskites can fill niches or pair with silicon to try to make better systems. One such path are these things called tandem solar cells. Basically, a tandem solar cell is two individual solar cells that are vertically stacked on top of each other. And doing this allows you to absorb more of the incident solar spectrum while minimizing the amount of losses you have, voltage losses, basically higher voltage with more current, allowing you to improve your theoretical thermodynamic efficiency limit from 34% to 42%. Perovskites are uniquely suited to these types of tandem architectures because, first off, their color, excuse me, the color tunability I alluded to earlier means that you can pair perovskites in ideally matched pairings with any choice of bottom material that you want. Secondly, the fact that perovskites don't require processing above 100 Cs means you can use these things called monolithic architectures, where you can deposit your perovskite directly onto a bottom substrate solar cell without having to worry about thermally damaging the underlying solar cell, at least not significantly. This has been a major concern for other types of thin film technologies that do require high temperature processing as they're attempted to be integrated in these monolithic designs. And it's important that we have monolithic designs like this because other designs require significant increases in balance of system costs to make them viable, and that's a no-go from a commercial perspective. I've done some work trying to do similar things with CAD-TEL perovskite tandem solar cells and shown that the promise of perovskite CAD-TEL, given the current state of both technologies, is not, it's perhaps something in the future that could be explored, but it's not very viable in the near or present term. The second path to commercialization, I believe, is to try to do things that silicon can't do, or at least things that silicon can't do well. Because of the thickness concerns and the vision of disruption I presented at the very beginning of this talk, you can think of perovskites as trying to fill this niche as well, used in permanently flexed or flexible designs, either in architecture, in commercial products, in a variety of different applications that silicon can't currently be used. Solid Technology, the company that has the video I showed earlier from 2018, they have a patent in Europe for a perovskite-based car cover. So, a cover for your Tesla that you could, put over your Tesla, and then there's a plug at the end of your car cover. You can just plug that car cover directly into your Tesla machine, or into your Tesla or electric vehicle, and charge it wherever you are parked, which is, I think, pretty cool. And I think largely startups that have been successful at developing perovskite solar are following down one of these two paths. Oxford PV is by far the gold standard of a perovskite technology. They have, I think, at least 10, possibly 100x the market cap of any other perovskite startup right now. And they're pursuing perovskite silicon tandem solar cells and have held the record for the last year or so, being the first company exclusively devoted to perovskite technologies to have held such a record. I've talked about Sala quite a bit in this presentation already. They're a Polish company that is trying to make this more ubiquitous, and they have more of the permanently flexed architectural designs that incorporate perovskite solar cell and more of a ubiquitous play. I listened to a presentation that they had 2 months ago at a virtual conference, and they've shifted their messaging towards less of the building integrated and less of the ubiquitous products and more towards Internet of Things applications and trying to power Internets of Things type of sensors and devices, which I think gives you a sense of where their funding is coming from and what their motivations are perhaps moving forward. Not only this, there's a lot of smaller players trying to emerge in the space, including Swift Solar in Washington, and in Dallas, Hunt Perovskite Technologies. I think it's very cool that you guys in Dallas have your own perovskite startup that is working with top American perovskite research labs at the National Renewable Energy Lab. I can't say much about them because they don't have that much public-facing information that I could find, but they're very exciting, and I'm excited to see what Hunt can do going forward. I think there's a third path as well to commercialization that people aren't talking about as much, but perhaps is in the mind of several. Perovskites aren't just great PV materials, they also have other types of applications outside of solar. particularly LEDs and display technologies can be made more efficient with perovskites, at least in theory. Interestingly, I recently found that Helio Display Materials is a startup out of the UK, but the same founders as Oxford PV that's trying to commercialize perovskite LEDs for these types of display applications. I think perovskite has a particular competitive edge when looking at blue emitting technologies. If you have a variable, if you look at LEDs across the spectrum, they all have issues with emission in the blue. And so I think that perovskites could potentially make very efficient blue emitting materials that could make your LED light bulbs and such way wider and less red. Beyond this, perovskites can be excellent photodetectors for IoT applications, radiation scintillators. I'm actually going to take a second to really emphasize this radiation scintillator thing. So radiation scintillator is basically just a detecting material. Perovskites are really, really good at detecting radiation, whether it's X-ray radiation or gamma ray radiation or any type of radiation you can think of. Perovskites are very, very good at this. They're actually less toxic than the current materials used, which rely on thallium for radiation detection. And I bet that within a decade, if there is market impetus to do this, which that's a question, but still, if there's enough market impetus, every radiation detection device that you'll be able to buy by 2030 will have at least some perovskite technology in it. Furthermore, other research groups have tried to use perovskites with varying levels of success for photocatalytic water absorbers or water splitting materials, spintronic materials for quantum information systems and quantum computing, and gas sensors as well. There's a hot off the presses article from Nature that actually has a different application no one's really explored before, and I think this is quite exciting. They used formamidinium lead iodide, you'll remember this acronym, a common perovskite, as an absorbing material for an artificial eye. Whether this can actually be used as an implant material or implant device is up for question because of the lead content, but nonetheless, even if it's only for robotics and other types of biomimetic materials, I think this is very interesting that perovskites have found this type of application as well in this type of artificial iris system with a large field of view. So in summary, do perovskites have a future? Will you ever be able to buy a perovskite? I think you can, but I think the how is still a bit unclear. Perovskites can either pair with silicon for 30% efficient modules, be used in flexible, flexed, or lightweight designs or silicon filters, including potentially in planes and other types of aerospace applications, which we haven't talked about earlier, where silicon panels are just way too heavy to really be used in these applications. So that could be interesting. And then also potentially perovskites could be used in other types of optoelectronic and other types of applications that are beyond solar, potentially moving to solar after large perfect deposition processes are optimized for these other systems. And with that, I'd like to acknowledge everybody who helped me with the research I showed and a lot of the research I did. My old boss, Brian Corgle, my current boss, Hugh Hillhouse, the Solar Energy Technologies Office of the DOE, who currently pays the bills, Equinor, and the Next Generation Photovoltaics Center, and the DOD, who used to pay the bills, and collaborators at Colorado State for work on the CAD-TEL project. With that, I'd like to thank everybody for their attention, and I will start answering some of the questions that I have seen pop up on chat, but I've chosen to wait till the end to answer. So thanks, everybody.
So, Tim, this is Michael, and if you mind, I'll read the questions to you and you can respond. Would that work?
I think that might work better, yeah, instead of me trying to read the questions off.
So
yes.
I'm gonna start off at the top, and this is a question from David Nowicki, and he asked, just to understand the principle on electrons traveling a distance and speed. The way I understand electron travel is each individual electron travels a short distance by traveling to the next atom, open, and so on. It's more like a long length of cars in a series. The first car hits the closest car next to it, and so on. The overall speed of the individual electron is relatively slow as well as the distance it travels. So the inefficiencies come from the availability of the next atom. So I guess the question is do you agree with this, this principle? Does he understand the principle correctly? Or?
No, yes, he does. The issue, though, is that's a good way of describing, from my understanding, metallic conduction. So conduction through metallic systems. Semiconductor systems are interesting because electrons in the dark, without any light absorbance, in semiconducting systems, you don't have a lot of electrons that are available. There's very few, in fact, so little that you don't have this chain reaction. So in a semiconductor, which actually was why semiconductors are used for solar cells, because without light, you don't have electrons, but with light, you do. And so I would say, to some extent, that is correct. But I think researchers tend to look at it from what we call an ensemble perspective, where we don't care about what each individual atom is doing. We care about what distributions of atoms are doing. So million, that's 10 to the 18th million. So like a million atoms. How are they responding to, or maybe just 3, whatever. How are they responding to external fields? How fast can these distributions of electrons move through the system and things like that? But yeah, I think that's a pretty good understanding of how conduction can work. So yeah.
Oh, okay. So the next question is from Mark Yoder, and he's saying, after 25 years, if these panels were mainstreamed, would the disposal of millions of lead-containing panels be problematic? Do they have the potential to be recycled?
Yes, there's a report from 2018 in, I'm going to go backward through that question. It can be recycled. There's this report from Environmental and Energy Science, which is the top sort of energy systems journal in the Royal Society of the UK, that shows that not only can perovskite solar cell panels be recycled, you can actually take lead from lead acid batteries in cars, which as we move to electric vehicles, that's going to be a significant problem as well, all this lead from these lead acid batteries that can no longer be used. And you can take that lead as well and do some chemical modifications that may be too costly. I don't know, but that's not our problem as scientists. No, that's a joke. But could potentially, you know, if cost was no object, you could recycle those that lead as well. I think using First Solar and their CAD-TEL recycling as a model, and that's much more difficult to do than in these systems, there is a way to recycle the lead from these panels at end of life. But again, it is problematic. It's something we have to think about and something we have to actually do and not blow off, because I think there's 2 different things there. Can it be done? Yes. Should we blow it off? No.
Okay. Thanks. The next question is from Ron Zagari, and his question is, would you expect perovskite modules or perovskite tandem coatings on carbon silicon modules as most likely to become commercial? And he followed it up with, yeah, you possibly answered that is where the next commercial, or what will be commercially available. Is that correct?
Yes, I think that the idea that perovskites by themselves trying to compete against silicon, I think is a losing proposition. There is a way that perovskites by themselves could try to beat silicon that I've seen. I don't know if I agree necessarily that this is the way to go, but it's by using perovskite tandems with themselves. 2 different perovskite materials and perovskite tandems. But as a standalone panel, as a single absorber, 1 perovskite in a panel will not ever beat silicon. That's my thought.
Okay. So I have a question before we move on, and that is, when they do become commercially available, what's their price point going to be? You know, like we always talk about dollar per watt or cents per watt on a module, relative to current, you know, cost. Is it going to be, you know, if it's 3 to 5 years out, is it going to be comparable to what we're paying for panels now because of this added technology onto it? Or what's your feel for that?
Yeah, So that's a very good question. I think the way, like, depending on it's interesting because you have to reframe if you take at a very technical level the individual components of the cost of a silicon panel, perovskite panel, they're very different. In silicon, the material is cheap-ish, and the processing is expensive. In perovskites, the processing is expensive, but the materials might be, depending on which ones you choose. Sorry, processing is cheap, but the materials might be expensive, depending on which ones you use. With the judicious choice of cheap materials and a good vertically integrated supply chain where you can synthesize your own materials on site, I think that the added efficiency of a tandem module will counteract the additional cost and lead to parity or below for in terms of not in terms of dollars per panel, but in terms of dollars per watt. I think that you could get cost reductions because of this.
Okay.
And I think it's particularly useful in systems where energy density is a problem, like on rooftops and in smaller scale systems.
So I have a question from Saul Bobst, who is asking if tungsten could be a viable replacement for lead due to toxicology, environmental concerns. Is there any research going on with tungsten iodide instead of lead iodide or bismuth iodide?
Okay, tungsten and bismuth are very different. The problem with tungsten is not, so you need a, okay, so for perovskite systems, at least the ones that are very well studied right now, you need a 2+ material, a divalent oxidation state. And tungsten is not easily formed in the 2+ oxidation state. It prefers higher level, it either prefers to be metallic or it prefers to be at a higher level oxidation state. This makes using tungsten particularly challenging for perovskite applications. Bismuth, despite the fact that it has the same problems as tungsten, is only one-off. It prefers to be trivalent, 3+. And so there's a lot of work with bismuth specifically, trying to see if you can, instead of using a single lead atom that's 2+, you could alternate each individual lead site with a 3+ bismuth and a 1+ something or other. That's been particularly challenging because you don't get the right absorbance properties you want. Or trying to move away from the cubic perovskites to materials that are close to perovskites but are not perovskites, but in the same sort, that have some of the same advantages. But turns out that when you put those in solar cells, they're not very good. There's a lot of research on bismuth, not so much on tungsten, because as I mentioned earlier, tungsten has the oxidation states that are stable for tungsten are too high. It's interesting to think about, though. I wonder if there's something there. I love these niche ideas of transition metals and things.
Okay, I'm going to move on. Actually, Dan had a similar question to what I asked with the dollars per DC watt. So sorry I took your thunder there, Dan. Then Ryan Clements, our host, can you touch a little bit more on silicon versus perovskite in terms of efficiency, temperature, and humidity?
Yeah. So efficiency for a perovskite panel is nearly at parity, at least on lab scale, with silicon. I'd say the record perovskite solar cell last time I checked is at 25.5%. Record silicon's at 26.5%. I think efficiency has reached parity, which is amazing given silicon is made in this very controlled process in a single crystal, and you have this polycrystalline
technical conference.
Okay. And
1 o'clock.
for the
for
the temperature and humidity concerns, temperature is I'd say they both favor silicon at the moment. I think thermal stability continues to be a concern with some perovskite material formulations, and humidity is certainly a concern that silicon doesn't have to deal with. Though a lot of the work I'm doing now at the University of Washington has shown that with judicious choice of encapsulation, we've made an argument that may have some flaws, but we're still working on it, that maybe the perovskite material could last in the field for a century. And so it's certainly less favorable compared to silicon, and that's never going to change. But potentially, it could it could be good enough. I'll say that. Yeah.
All right. So we're moving on to another question from, let me see, Robert Verkus, and he says, can the material be designed to absorb broadband sunlight and emit narrowband light? Interesting question.
Yeah. I would say, I'll do you one better. That's not a design feature. That is how it exists in nature normally. Normally, because of how semiconductors absorb light, they have this color. I call it color, but it's a band gap. It's just a vocab word. It doesn't mean anything. It's an energy, though. Every energy of incident light that the material sees, it will absorb. That if that energy is higher than the band gap energy. And then in a system that doesn't have a lot of these defect states, the material will then emit light narrowly at that band, or near, because there's some quantum effects, so maybe not at, but near that band gap energy. And so in normal systems, you actually have the ability to do this. Now, what's interesting in perovskite systems is you can get a single material that doesn't have narrow emission, but has a very wide emission. And so instead of traditional LED systems that have 3 different emitters, or 5, or however many colors you want to try to make a color neutral spectrum as you can, perovskites are being explored as a single emission white light source, which is something that not a lot of materials can really do. So the design is actually the opposite way, where it's instead of emitting at a narrow band, you're emitting at a wide band, which is something that very few other materials can do. So.
Oh, very interesting. Okay. Ajay has asked a question. First, he compliments you on a nice talk. But could you please comment on defect tolerance and how is it possible in solution process devices?
Yeah, I mean, this is a controversial topic. The way that I understand defect tolerance, and I'm assuming Ajay, because of the question you asked, is a little more technical, so I'm going to get a little in the weeds here, but just bear with me.
We're all nerds on this end too.
Yeah, so the way I see defect tolerance is because the perovskite is not a fixed lattice like in silicon, where all the atoms are basically fixed in place, but it's very dynamic and moving. Each of the atoms is moving around. I believe that the charged atoms react to, let's say, a single electron in a charged atom. Let's do the thought experiment. The charged atoms, because they're so mobile, can move to what we call screen these charges and protect them against the atomistic defects. That is my read of the literature. It is not, I would say, authoritatively the correct answer to that question, but I don't know if there is an authoritatively correct answer to that question right now. It's really, really interesting that we can get these super defect heavy materials that still somehow make really good solar cells. It defies conventional physical logic. So yeah.
Okay. Dan Lipinski asked another question, and he's asking, what are the remaining barriers to commercial manufacture of perovskite PV?
I think right now, that's a good question, because a lot of the challenges that on the public side I would think are challenges are being fairly well addressed. I think the major issue right now is trying to, is sort of trying to make these systems. Okay, I'll frame it in the way that I framed commercialization in this talk with the different paths. Path 1 with silicon perovskite tandems. I think the issue is to try to make large area solar cells that are cheap enough to deposit on top of silicon so that it can achieve parity with other types of generation technologies, and then hopefully beat it in the future as we ride the learning curve. With path 2, ubiquitous PV, finding a market for that type of technology where it's not just put it on the roof, hook it to the grid, but actually, something beyond that, where it's, filling a niche that that silicon is not filling right now because it cannot fill it. That's the problem, is how do you find a market where you can provide this power service at a good price point, maybe not a grid parity price point, but at a good enough price point, that is, and of whom it's receptive to using these kind of flexible technologies. I mean, I actually did an interview where I got roasted about building integrated PV at ARPA-E, which is, for those of you who don't know, it's like DARPA, but for energy projects. I was going to be a fellow there. And the thought with the building integrated PV, the major problem is how do you integrate that? Because actually connecting the solar cell to the electrical grid has been like a major issue when you put it into buildings. So there's all these niche challenges that come with niche applications, and that has been the major problem there, I think, is finding the market for the niche applications and then getting the cost and performance where it needs to be for the tandem applications.
Great, thanks. I have a question from Eugenia Katsigris. I hope I pronounced your name properly. Are you envisioning perovskite PV for large-scale applications such as grid-scale PV farms, or more only for small-scale applications such as, roll-up phone chargers, or, small residential projects, carports, things like that?
I've always been an all of the above type person when it comes to deployment of these things, and I think that as many bullets as we can fire, or as much stuff as we can throw against the wall, we should try to do it. And again, framing it in terms of path 1 versus path 2, this is kind of how I think about it. Path 1 would be the way to get into the grid and do grid scale applications. I think that's where the market is really big, and that's where the market cap, that we were talking about before the presentation, that's where that valuation might be coming from. As far as but I do think there are applications that could potentially pop up in commercial products and smaller scale applications, larger than commercial products, but other types of niche applications like that. And I think that it could find a foothold in either or both. But it's up to the actual developers and how the arc of history goes.
So I have a question. So Tesla automobiles, they have their pretty automated process, and when they do their painting, they actually dip the cars into a vat, right? Why couldn't that be perovskite cells when it comes out, the car's already a solar panel?
That's an idea that people are exploring. It's called dip coating. And so a lot of people are looking into that. There are interesting physics with dip coating that allow you to make more uniform films, theoretically, with spherical particles. But with perovskite, the problem with that is, so for paints, for example, you use really nonpolar solvents. And I don't know this for a fact. This is just me spitballing. But what I think the problem is that with paints, you have these nonpolar solvents that adhere to metallic and other types of surfaces very well. With perovskites, you have to use polar solvents, which don't have the same adhesion properties and therefore could really screw up how you deposit your solar cell if you try to dip it. So that could be a problem but with some surface chemistry, you might be able to overcome it. I'm not sure though. Yes.
So I have a question now from Joel Andre, and he actually has two, but I'll intermix them. And the first one is, whoops, hold on, I just lost him. Is there research or progress in using a transparent shielding coating for solving the humidity problem?
So encapsulation is something that, and that's more broad than specifically the transparent shielding coating, but all types of encapsulation are going to be very important for perovskite technology going forward. We're, in our group, currently doing work with encapsulation to show that encapsulation will have a much more outsized effect on stability than we even think as a research community. As far as research into the actual materials themselves, because of the great work that's been done in silicon and CadTel already, that is less prominent. We don't have as much research into the exact materials we have to use, because, I mean, everything that works for, if it works to block humidity from a silicon panel, what's to stop it from blocking a perovskite panel as well? But that's certainly going to be a necessary component of any commercial perovskite technology.
So we have a question from Mark Yoder. He's asking, how would these panels hold up to physical damage like hail or falling tree branches or things like that?
Yeah. So there's a couple points there. That's a good question. I think encapsulation will be very important for that as well. Design of the system beyond the solar cell itself is going to have the most outsized effect on how durable these things are to impacts like this. If flexible, let's say all perovskite tandems, let's say perovskite flexible tandems are the future and you can peel and stick them on your roof, it might actually, it really depends, because the materials themselves, if they're flexible, won't fracture like a silicon panel would. There's more give to them, which could, if there is a high, tolerance to this deformation, could lead to more stable systems, even without that even without a rigid encapsulation. So, yeah, I think that's interesting when designing systems and commercializing. I'm not, but I as more of a lab scale person, I'm not sure if I have a great answer to that.
I'm going to go back a little bit. I missed a question that was asked by AJ, a second question. I missed it. And so I'm going to go back and ask about that. And that's, you showed, and it's BI, is that bi-doping or is that actually boron iodide? Bismuth, okay, well,
yeah.
Doping to improve moisture stability. But at moderate humidity, it still didn't improve. How can this problem be overcome? Yeah,
I think the main point of that paper was identifying the problem exists, because I've seen so many studies, so many on perovskite materials and additives to improve stability, and no one considers for a minute that there's a difference in humidity stability when you age at high humidity versus low humidity. Like the idea that you have different effects at different humidity conditions, with these additives included, it's just something that the community doesn't consider as a possibility. And so that was the main point. As far as overcoming this issue, I think that a lot of the work I'm doing some cool work right now, where you try to use other ways to predict long-term stability behavior of perovskites that go beyond the 85 test used by the commission that does age testing right now. So I think that's finding alternative ways to get to these, to predict how fast these things degrade. That's going to be the important part. So.
That raises a question. In like today's environment with solar panels, they have like a 25-year performance guarantee of a loss of anywhere from 15 to 20%, right?
Yeah.
So if we have a commercial product and it has perovskite overcoating the silicon, are they going to, will that still have a similar type of production guarantee, or because they're slightly different materials?
No, you can't, if you cannot make the same, it's a dramatic mistake if you have a warranty backing up a claim that says that. You have to, your stability for such a system, because it is directly in series and you cannot separate the two systems from each other in a monolithic architecture, your stability is limited is a weakest link type thing, where you need to assess the stability of your weakest link, and that's the stability of your system. And so when you coat your silicon with perovskite, you have to reassess the durability of that system. So that's a good point. Yeah.
So we've got some great questions coming in. We have about 5 more. If anyone, we have time, and if you're still open, Tim, you know, hopefully you feel these are great questions coming in.
Yeah, no, this is
let
great.
You know that our audience is one, they listened and they're interested in this technology and going forward. What's in for? I just got a new question in, but let me go back. So Robert Verkus is asking. He compliments you again for a great talk.
Thanks,
my earlier question on bandwidth was about if one can make a silicon cell optimum by modifying the sunlight to be near monochromatic, so its efficiency is very high. Is that what the tandem cells sort of do already?
That's great.
No. So I really love that question because I'm super attracted to the idea of modifying the incidence spectrum. There's a problem though, and basically it has to do with the quantization of light, like going back to like Albert Einstein. So basically, the way you modify the incident solar spectrum, you can't do it in degrees. You have to do it from an energy perspective. It has to be like 1 in and 2 out with half the energy of the 1 in, or it has to be 2 in and 1 out, 2 photons of light in and 1 out with double the energy. It's very, very, very difficult to do that, and to do that efficiently, and to actually get improvements out of your incident spectrum, especially when you go up in energy, when you try to up convert, as they say. That is impossibly difficult, and people have been trying for a very long time. A lot of chemists are very, very excited about trying to do that. Tandem solar cell technology punts on that entire endeavor, and what it does instead is finds 2 different, it just basically plays within these current spectrum that you have naturally occurring from the sunlight, and tries to optimize the amount of electron and amount of electric power you can get from that. So yeah.
All right.
Yeah.
So I have a question from James Ornstein, and his question is, would it be fair to advise potential residential and commercial PV adopters that they should not postpone consideration in order to wait for cheaper systems enabled by perovskites? Because the consensus in the scientific community is that commercially available systems are likely too far away for the potential savings to justify waiting. So do it now instead of wait later. I mean,
I believe in decarbonization as fast as you possibly can, and that is what's going to be good for the planet. So do not wait. You might end up being an economic loser if you wait, but that's okay. Right now, silicon is still a great, like by itself, silicon still has great value. It maybe won't have as much value as if you waited, but it doesn't matter, because first of all, we don't know, this is still an open question. We don't know if. It's not about when. I think it's still kind of about if. And do it. Just do it. Get as clean, as green as possible, as quickly as possible. Let's do it.
I like your thinking.
Yes.
So I have a question from Dan Lipinski, and he's asking, encapsulants are infamous for breaking down over time due to heat and ultraviolet light. What materials are you exploring, and what is the life expectancy in actual use? So
that's a great question. And I don't know life expectancy and actual use of encapsulants. Again, we've just been banking on the idea that we totally steal everything that silicon manufacturers know and just like use it for perovskites. Right now, our major encapsulant that we use in lab is PMMA, but that is just so we can get these heuristic, which I think is very interesting, and hopefully want to publish a paper about this heuristic scaling factor. That says, let's assume PMMA is never going to degrade. Bad assumption, but let's assume it. What's the ratio of lifetime with and without the PMMA? That I think is the interesting question to answer now. And then once that question is answered, the next question becomes which encapsulant because we've kind of found they're all basically the same. Which encapsulant is going to withstand UV stress the best and help with that? So yeah.
Okay. Let's see. We're down to our last question, which is from Mark Yoder. And it also follows up on encapsulants. And it's, how much do encapsulants reduce efficiency?
I don't think that significantly. It absorbs some of the ultraviolet light, which you could potentially use this ultraviolet light, to generate electrons. But the ultraviolet light is also a destabilizing presence for perovskites. Now, I didn't mention it as a major one because I anticipated some level of encapsulant on top that would absorb this UV light or scatter it in some way, reflect it or something. And so it's going to cost you a little bit in efficiency, but it's very important to have anyway, because remember, I showed a slide earlier that showed how durability can drive costs down in the solar cell. So durability is a non-negotiable thing that is absolutely necessary. And so even though you have slightly less efficient panels because of it, and that happens for silicon too, it's definitely worth it, I think. So, yeah.
Well, that's our last question that was provided through the chat room. Does anyone have a question they want to ask personally? I have one more. If not, let me close. And I'm going to ask you, Tim, about, when I introduced you, we talked about what your interests were at the closing. And you're interested in machine learning to accurately predict degradation lifetime. So can you talk a little bit about that and what's involved with the machine learning process and what your discoveries there have been? And then we'll close it and turn it back to Rosa. So.
Yeah. No, so thanks for giving me the opportunity to talk about this, because this is first of all, this is somewhat new to me, because I've only been in this new position for about 2.5 months now, but it's very exciting. It's sort of a two-pronged approach, where we have this really unique experimental setup that allows us to take data throughout the entire trajectory of a bare material degradation, and then plug the data that we collect into a very simple machine learning model. I'm not a machine learning expert. I'm a novice, and to even say that might be an embarrassment that people actually know things about machine learning. But even I can write a simple machine learning algorithm that takes the experimental data that we have at very early times, like the first 5 data points in this hundreds of data points degradation curve, and predict within certain ranges, trying to narrow that range even more, but predict within certain ranges for new materials, like do forecasting and say, okay, this material will degrade in this amount of time based on all the machine learning that we've done on the older materials that we've already put into our system. We're going to now transition and try to move towards device level work with much of the same things, where we take data from early time, various different types of data, and try to use that to predict when certain device characteristics like current, voltage, and efficiency start falling. And so that's the really cool part, because it can give you, it can tell you within 5-10 minutes, okay, this is a solar cell that's going to last 12 hours. This is a solar cell that's going to last 20 years. This is the kind of predictive power that we're hoping to achieve with this project that we're doing, is to give you really rapid, given certain aging conditions, give you a rapid sort of prediction on what kind of stability behavior you can expect to see in that specific device. Because this is something that even in a generic device, no one really has the answers to yet. So, yeah.
Well, that sounds exciting, because that actually, depending on results, you might have a commercial product viable at an earlier date.
Exactly. And you can have more confidence in your wild claims about stability that you have in your press release videos if you're a startup company.
Exactly. All right. So thank you, Timothy. I mean, you did a fantastic job. Kudos
thank you.
to everyone. We appreciate it. This has been recorded. It'll be available on NTREG's website, and I believe you recorded it as well. So please spread the word. This fantastic research and technology going forward. And so I turn this over to close with Rosa. Thank you, Rosa.
And thanks again for having me. It's a real honor to be here and to present my work in my field to anybody who will listen. So thank you so much.
Dr. Siegler, we want to thank you, and we've been getting a lot of great comments from the participants about how much they enjoyed and learned from your presentation. We want to thank you for sharing your knowledge with us. I want to again thank everybody who has participated. And Joella, if you're still